Hi, hello everyone. Thank you for joining this webcast today. We're going to cover this exciting topic on how to deploy secure and scalable Kubernetes apps with Tanzu service mesh and Ingress services. First of all, I'd like to introduce our speakers. We have two speakers, Manish as well as Bhushan, and hopefully you guys all celebrated a Pi Day a few days ago. We'll have this quick say hi. Manish and Bhushan, would you like to introduce yourself real quickly? Just see your role and what you have done in the past in the industry.
Oh, sure, Lee. Hi, guys. My name is Manish. I'm an enterprise technologist in the Office of CTU in NSBU division of VMware. And prior to that, I was actually the CTO of cloud at RV Networks, which was bought by VMware a couple of years back, and then got actually converted into NSXALB, which is something which we're going to be talking about today. And it's nice seeing you all here.
Hey everyone, my name is Bhushan Pai. I'm a senior technical product manager with the AVI team in NSBU. And yep, we'll go over today's AVI integration with Tanzu service mesh.
Yeah. My name is Lei Yan. I'm the Senior Product Marketing Manager here. I'll be your moderator for the day. Now, before we begin the exciting PowerPoint presentation as well as a live demo, I'd like to just lay out a few ground rules. So first of all, this webinar is being recorded, and we will send out the recording as well as slides at the end of the day, hopefully. And you guys can, if you find the content to be useful and you have coworkers who couldn't make it to the live time, you can watch the on-demand video. So feel free to forward the email along. Second of all is you can use the Q&A panel that's in the GoToWebinar control panel and type in your questions. We'll answer offline. I will also read some of the questions live towards the end of the webinar. So we will allocate at least 10-15 minutes at the end of the webinar to address any questions you have. All right. Okay. So without further ado, we have a packed agenda. I will let Manish take it to the agenda. Okay.
Surely, thank you. Okay, let's take a look at our agenda for today. We'll start off by talking about a journey which we all are a part of, and that's to do with digital transformation, and more specifically about how application transformation has become a key to this journey. But like most of the transformational efforts, this also comes with its own challenges. In this presentation, we'll try to dig deep into some of those. We will also talk about how VMware's Tanzu service mesh, along with its features and integration with RV, which is NSXALB, is helping enterprises overcome some of these challenges, both at east-west and north-south layer. We will also look at some of the use cases in detail. We also plan to spend around 20 to 25 minutes doing a live demo, right? So hoping and praying to the demo god that it works fine. Yeah. To start with, a customary slide about how applications and infrastructure both have evolved in the last few decades. I'm sure we all know about it, and we have been seeing this happen in the last couple of decades or so. In the beginning, we used to have big monolithic applications, which used to run on bare metals in the data centers, and we used to have application services like load balancers, which were manually configured on the fleet of appliances, right? This was a mode of application deployment, which is primarily seen in late 90s or early 2000s. This evolved as applications become more virtualized, and the concepts like public cloud or infrastructure as a service came into being. In the last few years, we have seen, especially in terms of application evolution, we have seen a major shift towards microservices architecture. In the microservices architecture now, that monolithic function, the monolithic app that we were talking about is broken down into small individual services, which can be built, deployed, and managed independently. We don't want to go deeper into the benefits of microservices architecture as a part of this presentation. It's very well documented, but let's touch upon a few. First of all, it gives your teams developing the microservices complete independence on how they deliver a feature with minimal dependency on other teams or services, right? So the independence is what the development team gets, right? They can choose the appropriate technology they want to use, they can choose the programming languages they want to code in, and so on and so forth, right? Since this helps limiting the scope of changes and reduces the amount of coordination between the teams, you can now start releasing more frequently, right? That's the benefit you get from the development point of view, right? From the operations perspective, it gives the flexibility to upgrade only the services that require the update, for example, right? And for example, let's say a feature only requires a change to a single microservice, then that microservice can be rolled back without affecting the workflows of the other team. You can also scale these microservices independently, right? So it enables operators to scale each services according to its workload demands and the needs or the performance needs per se. So in summary, it has really helped enterprises to deliver scalable and resilient systems with improved time to market, right? So those are some of the benefits, right, that microservice architecture is providing to the enterprises. But as I said in the beginning, right, it comes with its own challenges, right? First of all, decomposing a microservice or decomposing a monolithic application into a microservice results in the distributed systems. Now, application and platform teams both need to manage different aspects of communication between many of these discrete services or discrete microservices that are running in a cluster. For example, how do you do traffic management, which means how do you connect these microservices? How do you route between these services? How do you load balance? Or even how do you secure communication between these distributed microservices? So operational issues regarding how do you reduce latencies between the service chain, which can ripple across entire application and affect the user experience. In terms of observability, how do you observe what's going on? It's like a black box, right? There's so many microservices communicating with each other. How do you establish and maintain operational visibility into the state of the microservices? And last but not least, how do you troubleshoot and identify the root cause of the problems, right? In an application which is like completely distributed into many of these microservices, right? So these are a few of the challenges that we are seeing. Also, what we are seeing is when we are deploying an application as a microservices architecture, it's normally not only deployed on a single cluster. We are seeing that enterprises are increasingly moving their application to the cloud and commonly choosing to deploy their application on multiple platforms or multiple clouds. This is challenging, right? This is challenging because each of the clusters or clouds is like an operational silo. Since each of these clouds has its own operational model and also set of tools that have been built since many years. So not only do we have to manage the challenges of distributed architecture that we just talked about, but also we need to now do it in a very consistent and seamless manner that works across clusters and the cloud boundaries, right? So those are the challenges that we had with the distributed architecture has manifolded because of the fact that we tend to deploy it in multiple clusters or multiple clouds. There are multiple reasons why customers or enterprises are actually choosing to deploy it in multiple clusters or clouds, right? When we talk to our customers, this multi-cloud, multi-cluster pattern is becoming more common, right? We typically see our customers having 2 to 3 clouds, some including a mix of on-prem and public clouds. Now, the reasons for choosing a pattern like this are various, right? Some of them have to do with isolation. For example, whether it's a tenant separation, reducing the blast radius, or for implementing a business continuity pattern like high availability or DR. Other reasons could be purely based on location. For example, addressing locality compliance or latency requirements, right? But there's another reason which is quite interesting and that we are seeing from the customers and it's related to the fact that not all the monoliths have been transformed into microservices. This is mainly the case with stateful applications. And these critical applications are running in a separate VM infrastructures in VMs, right? Now, even though these customers are moving to the cloud native applications, they still need to coexist with the traditional applications which are running in the VMs. So you need to have the connectivity between the containers that are getting modernized to these VMs, which are critical. And the whole application is a mix of both of them, right? And we believe that this is likely to remain there for an extended amount of time. So this is another reason that people choose to actually deploy it in not only different clusters, but also in different infrastructures. So why can't we solve this using a traditional application or networking model, right? These challenges used to be there before, but now the challenges have changed. They have changed because of the pure nature of the fact that microservices are dynamic in nature. right? The main reason is that the identity of the microservices is dynamic. It's not based on IP addresses and ports. And the boundary of the services is not limited to a node in the data center or even the data center itself, as I said, right? It's going across clusters. The traditional networking and security model is centered around this type of static identity, right? And location, which is about IP addresses and ports, right? In the highly dynamic and complex world of microservices, we really cannot think about networking and security simply through this traditional lens of IP. And that is where service mesh comes into picture. Most of the challenges that we talked about are being solved by a pattern called service mesh. It can be seen as an infrastructure layer, which can handle challenges around service discovery, connectivity, observability, and also around policies, whether it's to do with traffic management policies between these services or security. It primarily provides the services on a container-based platform like Kubernetes, but it can also be extended to other non-Kubernetes infrastructures like VMs or serverless. And we'll see that in our presentation on how some organizations or some solutions extend it to VMs, right? Including the one which VMware has. Now all this features of service mesh that we just talked about that service mesh provides, right? It's actually abstracted from the developers using an architecture where the communication between the services happens through the sidecar proxy. If you look at this slide, this is dominantly the architecture which most of the service meshes out there have, right? Where the communication between all the services happens through the sidecar proxy, which sits alongside each service. In a container-based platform like Kubernetes, this sidecar proxy is another container deployed with the service container in the same Kubernetes pod, right? The traffic from and to the service flows through these sidecars, right? And this corresponds to data plane. And these sidecars are managed and configured by a centralized control plane, which configures traffic routing and policy and does policy enforcement and so on, right? With this architecture, we can easily implement and configure platform services, which we talked about, like service discovery, connectivity, security, observability, and so on, right? Without the need of changing the applications. Remember when I was talking about application services like load balancers getting more and more distributed? This is the kind of pattern I was referring to. But even with this, there are certain challenges. How do we provide features of service mesh to applications which are distributed across multiple clusters, clouds, or infrastructures? We talked about that. We talked about the pattern that enterprises are using these days, right? So how do you provide these features across multiple clouds and clusters? This is a real challenge that enterprises are facing in this complex world today. And also what enterprises care about is just not service-to-service communication, but more about their users who are accessing their services, and also the kind of data that is being accessed. They want to secure that access, right? They're looking for solutions which can help them deliver a great customer and end user experience while securing the service access to the services and securing the access to the data, which is sensitive to them, right? This is what we are trying to achieve with VMware's offering of service mesh, which we call as Tanzu service mesh. Where not only are we providing the de facto features around observability and security and so on, right, for a single cluster, but extending it to multiple clusters, clouds, and infrastructures, including VMs. So in a way, not only are we focused on the future, but we're also meeting applications where they are currently, right? To know how TSM is able to do this, let's kind of look at this high-level architecture. At the high level, TSM has a global controller. It is a SaaS service to which customers can onboard their Kubernetes clusters, which could be running anywhere, right? For example, it could be a TKG cluster running on-prem or on cloud, or an Amazon EKS or a GKE cluster, to name a few. Once connected, the global controller deploys a local control plane on each of the clusters, which delivers fault tolerance in the event that if a cluster becomes disconnected from the global controller, you're still up and running. It also deploys the data plane components, which we just talked about, which are the sidecars that are deployed alongside the application in the service mesh, right? And these are the sidecars which actually handle east-west traffic inside the mesh. With this architecture, global controller delivers differentiated control, security, visibility, and auto-scaling capabilities through these sidecars. One of the primary concepts and constructs that Tanzu Service Mesh has is the concept of global namespaces. We'll spend some time on this because this is a very important concept. Let's dig a little bit deeper into this, right? What GNS is it allows developers using Tanzu Service Mesh, regardless of where they are, to connect application services without having to specify any underlying infrastructure details. And all of this is done automatically. So what you can do is you can actually deploy your services into GNS from different clusters or different infrastructures, different namespaces of multiple clusters or clouds, and so on and so forth, right? With this powerful abstraction, your application microservices can now live anywhere, right? In cloud, allowing you to make placement decisions based on application and organizational requirements, right? So you're not tied to an infrastructure constraint. You can also think of global namespaces to be some kind of an application boundary, right? It provides strong isolation for an environment for application teams and business units, which are managing these applications and data. Sometimes we kind of like to call it a slide of service mesh across clusters because it provides you all the service mesh functionality, but it slices it across the boundary of clusters and infrastructures. To double click a little more into the features and capabilities of DNS, as I said, regardless of the location and services, a global namespace manages the following functions, right? It provides the identity to the resources that are a part of global namespaces, which are the workloads or the services. Each global namespace has its own certificate authority that provisions identities for the resources inside that chain. It provides discovery. It controls how one resources can locate another and provides some kind of a service registry, right? If we want to call it that way. It enables policies on the resources within the global namespace, whether they have to do with connectivity, like how the communication is established between the resources, and also security policies. For example, if you want to encrypt the communication, you can define the security policy to encrypt the communication, and so on and so forth, right? Global namespace also creates a service graph of all the resources that are connected within the global namespace, right? And it does that by collecting a rich set of telemetry data, such as metrics for services, for your clusters, and for your nodes, right? That is what enables us to show a real-time graph, service graph, or it also is used to define policies like SLO and auto-scaling based on those metrics. As I said, global namespaces is kind of an isolation boundary, right? So no services from outside the global namespace can talk to services within the global namespace and vice versa, right? Now, to expose a service outside a global namespace, what you need to do is you need to create something called a public service, right? You need to define a public service within the GNS. As soon as you define a public service within the GNS, we automatically go and configure the load balancers for you, the DNS or IPAM. We also configure regional or global load balancing depending on whether the service is distributed or running across regions or across clusters, right? Now, for us to enable this use case of public service, as you can see, we have dependencies on load balancers, on DNSs, on GSLBs, and so on, right? Now, we can enable these use cases by having multiple solutions provide these features and functionalities, in which case it involves users to manage and operationalize multiple such solutions, right? But what we also do is we provide a one-stop solution with Avi, which is our enterprise-grade load balancer, because Avi provides all these capabilities and more out of the box in a single solution, right? You don't need multiple of such solutions to enable use cases like this, right? But before we get into those use cases of Avi and TSM together, let me invite Bhushan to give us an overview of Avi. Hey, Bhushan.
Hey, thanks, Manish. Yeah, so just like Manish was saying, the Tanzu Service Mesh is really good at providing consistent security, app security, connectivity, and resilience across the clusters. But for exposing these applications to external clients, you need a load balancer, and that's where Avi comes in providing layer 4 load balancing, Ingress controller, GSLB for load balancing across sites, on-prem and public cloud, and even web application firewall for security. Yep. Manish, can you go to the next one? Yep. So what are these Ingress services that are required? Basically, it's not just the traffic management. There's other things like managing the traffic within the site as well as across multiple sites. You need path-based routing, request routing. You need integrated IPAM and DNS to operationalize this easily. SSL termination and certificate management to secure your front end. Other things in security like network policies, ACLs, DDoS protections, web application firewall, and all of these needs to be tied together into a single observability platform so that users can debug whenever something fails or some error occurs. For this, we integrates with Tanzu Service Mesh and also the Antria CNI that VMware supports on all of its Kubernetes products. Yeah, let's go to the next one. Usually in a traditional environment, DevOps people can do this using a disparate products like a different LB, different solution for GSLB, different one for analytics, WAFs, IPAM, DNS. Usually people even manage the IP addresses manually and program the DNS manually and have an Excel sheet to correlate both of this. All of these can work in a lab environment, but when you go to a production case enterprise environment, all of this falls apart. You need simplified operations, application security, app availability across multiple environments, and on-demand elasticity to provide good user experience out there. Let's go to the next one. Yeah, so like we said, on a traditional environment, the way this is realized is you deploy an Ingress controller inside your cluster to handle the layer 7 services and path-based routing and all. Then you need an external load balancer to load balance across these Ingress pods across multiple nodes of the Kubernetes cluster. And again, if you have this across multiple sites, you also need a third solution, a third product for GSLB. And there's also always the DNS and IPAM requirement for service discovery to the external clients and extra security by WAF. All of these are like discrete multiple solutions which will have their own complex ways of operationalizing things, and bringing them together makes the operations really complex. Each one of them might have their own dashboards, and bringing them together makes the observability really difficult because you don't get an end-to-end picture of what's happening. Opposed to that, what Avi provides is a consolidated single solution, which provides everything right from layer 7 Ingress, layer 4 load balancer, a web application firewall, GSLB, DNS, and IPAM in a single solution with a single license, providing operational simplicity using its automation, rich observability, which gives you end-to-end observability all the way to the pod, from the client to the pod, and cloud native automation. Everything you can directly configure through your Kubernetes, and the Avi controller will realize it for you. So let's go to the next one. Yeah, just a quick overview of Avi's architecture before we move on to more TSM related stuff. So Avi has a very modern distributed architecture. Unlike any other load balancer in the market, we have a centralized control plane which manages all the configurations and gives the user a single pane view of all the load balancing configurations, while the data plane is called service engines, which can scale elastically independent of the controller. So it gives you a user a single place to configure everything while managing the elastic load balancing fabric across multiple clouds, across multiple ecosystems, right from bare metal x86 box or a virtualized VM format on VMware, or even containers both in public cloud as well as on-prem. This allows can you go back? Just one more point. out there. Yep. So the AVI controller has inbuilt automation to bring up the service engines and automate the load balancing provisioning for you. So and this, as the traffic flows through the service engines, it collects hundreds of different metrics and analytics, which gets displayed on the AVI controller in various graphs for each and every, so for each and every ingress and each and every load balance service that you create on a Kubernetes side, you get really in-depth analytics on AVI controller. So yeah, that was the summary of AVI controller. Let's see it in action in some of the use cases of how this is being used with Tanzu service mesh now. Back to you, Manish.
Perfect. Thank you, Bhushan. Yeah, hi guys. With this high-level understanding of Tanzu service mesh and AVI's architecture, let's have a quick look at some of the use cases that they enable together. Right. At a very high level, we categorize them into two different buckets. One around app continuity and service bridge, which enables use cases like multi-cloud or hybrid cloud connectivity using GNS, as we just talked about. It enables use cases around high availability and DR patterns with AVI, and we're going to look into that very shortly. And also around application migration and service bridge, right? This is something that is going to come soon. This is not there as of today, as a part of which we can extend Tanzu service mesh into apps running on VM-based infrastructure, right? And we do all of this using our integration with AVI, right? The second bucket is around app continuity and resiliency. This enables us to define app service level objectives and policies around it. You can measure application performance with a configurable service level objective. And as application demand changes, you can auto-scale services to maintain the service level objectives using TSM's autoscaler. This intelligent auto-scaling feature of TSM along with AVI also enables us to provide use cases like cloud bursting and so on, right? Let's take a little deeper on how TSM with AVI enables each of these use cases, right? In this slide, you can look at a high-level architecture of how TSM and AVI looks in the use case of high availability or app continuity, right? In this slide, you can see there are two Kubernetes clusters. One is running on-prem and one is running on cloud. They could also be running in two different regions. We have AVI controllers for each of these sites. So let's call them sites. We have AVI controllers for each of these sites. And an AVI controller is configured to provide GSLB across the regions, right? AVI controller also has the service engines, which are the load balancers, right, which Bhushan just talked about, for each of these sites. And these provide L4 load balancing. And on top, we have a TSM global controller in the SaaS, which manages both AVI as well as the clusters that are onboarded onto the global controller, right? With this setup, what we can now achieve is once you have applications deployed on both the sites, on-prem as well as cloud, and you want to expose one of your microservices, let's say one of your front-end microservices to the outside world using a public service construct, right? You can do it within a GNS. You can put all these clusters in one GNS and expose one of the services as public service within the GNS, which ultimately goes automatically and provisions AVI to configure DNS, to configure L4 load balancer, so that this application is accessible from outside. And the fact that if this application also resides on the other cluster, on the other site, it automatically also programs the GSLB for you, right? All of this happens automatically as soon as you provision a service to be publicly available, right? That is the whole magic of these solutions working together. And of course, we do health checks, not only to the gateways, which are the endpoints of each of these clusters from north-south perspective, but we do health checking to the actual service behind the scene. And we have some intelligent algorithms which actually look at the headers within their health check requests and so on, right? To make sure the health checking is done to the end service endpoint and not only to the gateway, which means even if the service behind the Ingress gateway goes down and Ingress gateway is still up and running, we will be able to detect that the service is down and fail over to the other side, right? Based on whatever load balancing algorithms you have configured. Apart from the fact, of course, yeah, if the whole cluster goes down, you will anyways fail over, or if the whole site goes down, including AVI controllers on that site, we are still up and running. So this provides you not only app continuity from service perspective, but also disaster recovery from a site perspective, right? If a site goes down. We also have SLO as a feature, which you can configure on the service. And these SLOs are action level SLOs. So as soon as the SLOs are about to get violated, we can set actions to auto scale our application services, right? And this could get triggered by, for example, a lot of traffic being sent to a certain cluster, and the load increases, so does the service level indicator, and hence our applications need to auto scale. And this auto scale happens automatically based on the auto scale configurations that we set. Now, in some cases, we don't want to just auto scale in single clusters, right? Because at some point of time, you will hit the resource consumption of that cluster. What you want to do is you want to actually auto scale across the cluster. You want to actually create another cluster and deploy this application onto that cluster and scale horizontally that way, which is also known as cloud bursting use case, if you're auto scaling it into the cloud cluster. We enable that use case automatically because of GNS, right? So as soon as we figure out that a particular cluster is crossing the limits of the resources, you can have another cluster as a part of the GNS and deploy an application on that cluster automatically or even manually, right? And as soon as the application gets deployed on that cluster, we automatically trigger the configuration to RV to provide GSLB across these clusters, right? So that is a very important use case that we achieve using this integration. Another thing that we do as a part of this is, and this is an upcoming feature, is not only do we utilize the GSLB as one of the solutions for high availability, we can also have a tiering model where the original load balancers that you see here can act as L4 load balancer, and you can define policies per regions, which are different than the GSLB policies on top, right? We can do all of that. And apart from that, you can also configure these load balancers at an L7 level, which enables some use cases like providing wireless application firewalls to public services and so on and so forth, right? So it kind of builds upon that zero trust security model from north-south, where you can enable security at L4, L7 load balancers. At the Ingress level, have features like WAF, you can do east-west communication encryption, and so on, right? So it builds on that zero trust foundational model. At this time, without much ado, let's jump into the demo. Okay. So for this demo, what we have is we have 3 clusters here. There are 2 on-prem, and we are kind of replicating what I just mentioned in the use cases slides, right? We're trying to replicate that. So we have 2 clusters on-prem. We have services already deployed on these 2 clusters. We'll get into that. We also have another cluster on the cloud onboarded onto Tanzu Service Mesh. So this is a cluster overview of Tanzu Service Mesh. To onboard a cluster is actually pretty easy. You just add a new cluster here. You generate a security token, apply these couple of YAMLs onto your cluster, which deploys an agent into your cluster, which calls back home to the TSM SaaS. And then you can see this connection happening here, and then you can install Service Mesh onto the cluster. And as soon as you do that, it takes a couple of minutes, your cluster is in this shape. This is a brand new cloud that I onboarded. It has no services running within it. Now, what we have deployed on these clusters is an app, which is a shopping app. It's called Acme Fitness app. It's comprised of multiple microservices. It's a polyglot application. There's a shopping, which is kind of a front end. There is cart, order, and so on and so forth, right? There's a little bit of twist, though. One part of this application has been deployed on another cluster, and that is the catalog, right? And these are completely 2 different clusters. There's no connectivity as such between pods between these clusters, right? So if we try to actually look at this service, let's try to, since we have not still created a global namespace or exposed this using a public service, let's try to port forward the shopping application, which is running on this cluster, and see what we can see. So it's localhost 3000, And there you go. You can see the shopping application. This is the Acme Fitness application that we talked about. So you can go to cart, but the problem is you can't see anything, right? There is no catalog because catalog is running on another cluster, and there is no connectivity between that. So this is the state where we are in right now. We can, if you can see, we can see a spider graph or a service graph here, where we have a load generator already running just to make sure that there's traffic always there. This shows you the connectivity between all the services. You can hover over each of that. It shows you kind of golden metrics of what's going on with that service. You can get the details. You can also click each of the service, which gives you the spider graph of that particular service. You can also see the node heat map, which kind of helps you correlate if anything is happening on the nodes where the service is running, in case there are any issues, right? So that correlation is really, really helpful. And there are many more graphs and charts that you can look at, and we'll get into that a little later. But let's also look at what other things we have configured as a part of this demo. What we have is integration with RV. So we have RV configured, and RV is, and we'll get into that. RV is configured as into multiple sites, into both on-prem as well as cloud, as two controllers, and it has GSLB configured, right? Or once it's configured as GSLB, the only thing we need to do in Tanzu Service Mesh is add an integration where you just give it the credentials and the IP address of the connectivity to the leader of the GSLB, right? That's all you do here. And if we log in into RV, we will see there are no GSLB services right now, but RV is configured to provide GSLB. And there are two sites. There's one on-prem, there's one on the cloud. The on-prem one is a leader, the other one is active, and it's a follower. And you can also see we have provided two subdomains which are delegated to GSLB. One is called tanzuservicemesh.net, and the other is tanzuservicemesh.com, right? We have also defined a SLO feature for our application, in which we have created a front-end SLO definition, where we are saying, hey, you know what? I want my service level indicator to be set as P99 latency, which should be less than 300 milliseconds, P99 latency. And our SLO is set to meet these conditions 90% of the times, right? Which gives us a monthly error budget and so on and so forth, right? If you edit the configuration, you can see you can even set P50, P90 error rates and so on and so forth. So there are multiple things that you can set in here, and then you can set on which service or the group of services you can apply this SLO on, right? So for this demo, we have set it to be applied when P99 latency is less than 300 milliseconds. So as soon as it crosses 300 milliseconds, our SLO will start getting to warning and start getting to violation if we get done with our error budget, right? So that is our SLO setup. Now let's go and create our GNS. Let's call it Acme. Let's give it a domain. And as I said, a GNS provides an identity for all the resources within GNS, and that identity uses this domain. So any service or workload within this GNS will use this domain for east-west connectivity and communication. Yeah. Let's call it acme.com. Let's go in here, and this is where you define what constitutes your GNS. This is a rule-based model. So you can add your clusters here. I can add clusters and namespace where the application is deployed. If there's an application deployed, you will see all the services that are deployed in that application. I can add multiple clusters. So let's add the second cluster here. And let's also add the third cluster, even if we do not have anything deployed there. As I said, it's a rule-based engine. So as soon as anything gets deployed on EKS Cloud in Acme namespace, it will automatically become a member of this GNS. Once we do that, this is where we can configure a public service now. Let's configure shopping, which is our front end. You can see our ports automatically got populated. And this is where we configure how you want to access the service. So this is where you give your public URL. You can also see that we've already populated, and we're already talking to RV, we populated the subdomains that were delegated to RV, right? So we saw we had two, and that's already gotten populated here, and we pick one of them, and our application should be accessible on this, right? We define health checks. For this demo, we'll define default health checks. And in configuration summary, we can see what we did. So we configured a public service, we configured service mappings, we configured a health check. Now let's do finish. As soon as we do this, you can see what we have done behind the scenes. Is there was no GSLB service, right? We have already configured a GSLB service in RV. And we have added an endpoint to the first cluster where this application was running. It'll take some time before the health checks determines that the service is up and running or this cluster is up and running. But what we do behind the scenes is we configure a set of service entries. So we are on the on-prem 1 cluster. Yeah, so if you can see, we have service entries configured for all the services, including the catalog, which doesn't even exist on this cluster, exists on the other cluster. And this service entry is which points to the gateways using which the communication happens across the clusters. So we have already plumbed gateways, egress gateways on this cluster, ingress on the other clusters. We've plumbed the DNS behind the scenes automatically so that when a service wants to talk to each other, for example, if shopping wants to talk to catalog, right, using this name, it can reach to the egress and ingress and ultimately to the service running on the other cluster. If you look at the shopping deployment, let's do it for catalog. And let's look at all the deployments that we have. Yeah, so we look at shopping, and sorry, I missed to actually print the YAML. Let's look at the catalog. And you will see that shopping is reaching catalog where catalog.acme.com, right? So everything is automatically provisioned and configured behind the scenes. So the only thing you did was configure a GNS, expose a public service. And now when we actually try to access this service, now try to access this from the external URL, right? Let's do that. And you can see, we can access the complete service. You can now see the catalog, you can see all the products and so on, right? So now you have access to a complete application, and this worked automatically, right? So you could see how intuitive this was. You just added a GNS and everything just started working, right? And if we go into the service graph, now in the GNS construct, initially we were looking at the cluster view. If you look at the GNS view, you can see we already have a service graph in the GNS view, where you see 2 clusters and you see shopping is talking to catalog. And by the way, all of this is encrypted, right? There's an MTLS between all the services within and across the clusters, right? So this is cool, right? So things automatically start working in the GNS, and you've got a graph where you're seeing how services are talking across the clusters. And everything is all good and everything is fine, services up and running, right? Now let's try to increase the traffic. And see if we can have an effect on the SLO definition that we had, right? So here we are actually having a load generator generate some traffic, at this time externally to the external public URL. So let's do that. I also want to show you that we have autoscalers already defined for this demo. We have autoscalers for each of the services in a certain mode, but they are not enabled right now, and that's because we want to show SLO getting violated, right? And we'll enable it later once the SLO gets violated. But in normal scenario, you will have it always enabled. And in that case, you're kind of guaranteeing the SLO. So as soon as it reaches the SLO threshold, we will automatically, before even that, we will automatically autoscale based on the configurations and guarantee the SLAs, right? Now, if we go back and look at our graph and click on shopping, let's try to look at the performance tab of shopping. You see the SLO is green, right, till now. There are and it shows the SLIs. RP99 seems to be within the range. At this point, you can also see that we are not auto-scaling, right? Even though if we have set the auto-scaling, we're not auto-scaling because everything is disabled and we don't need to, by the way, at least at this point. But as requests are increasing and the traffic is increasing, you can see that the requests are increasing, the request count is increasing, our P90, 99 latencies are increasing, right? You can set P50 latency here. You can define what you want to see in this performance tab, right? But as our traffic increases and our P99 latency increased, you can see our SLO started turning orange, which means that we have started depleting our error budget, and you can see that happen here, right? We are burning our error budget as P99 crossed the limit that we had set, right? And as the traffic will continue to increase, our error budget will continue to deplete, and SLO will get violated, and it will turn red. And this is how you basically can monitor your SLO and see what is happening with your SLO, whether it's getting violated or it's still under warning, and have actions, or have automated actions like I just said, right, by enabling auto scaling. So let's go and at this point enable auto scaling. So yeah, let's enable auto scaling, and you can see these getting auto scaled. The enables getting true, changing to true. And you can also see here that we've already figured out that since we've increased the traffic and our SLO has gotten violated, we need to increase the instances of each of these services. We did not increase it because it was not true. Now, since it's enabled, we will start increasing, right? Before we get back and see what is happening behind the scenes in the performance chart, let's look at one of the definitions of the SLO. Right? Let's look at the shopping one. I call it ASD front end. So if you see the definition, it's pretty simple. What you define here is the mode. Currently, the mode is efficiency. We also have a performance mode where we actually define that you always auto scale. In efficiency, auto scale and scale down if the traffic reduces. You define the min and max instances, and you define the metric and the scale up and scale down condition. In this case, we said 300 milliseconds to scale up, and if it falls below 50 milliseconds, scale down, right? There are other metrics that you can define based for example, in this case, payment. The trigger is requests per second. For order and cart, the metric that we're looking at is CPU usage. There's memory usage. There are other latency parameters, and all this is all a rich set of metrics that we get from Tanzu Service Mesh. Now let's get back and look at what is happening behind the scenes. We see that SLO actually was violated as we were showing you the auto scaling definition, and it turned all red. But as soon as we enabled auto scaling, we are seeing that things will start auto scaling now. And as things start auto scaling, and you can already see that our instance count has increased now, the SLO will automatically turn green in some time, right? And there it goes, right? So SLO has turned green. Our P99 latency has gone down, and we are doing all good here, right? So this was the auto scaling feature, but there's a limit to which auto scaling can do, as we discussed in our use cases slides, right? We can keep on auto scaling this, but at some certain point of time, you will actually hit the limit of your cluster, right? At that point of time, you want to enable use cases like cloud bursting. So let's try to do that manually, just to showcase what happens behind the scene. So let's assume that we did hit the auto scaling limit, right? And we want to automate going to the cloud now. So let's go to the cloud. Right, so in this cloud, we have nothing configured. So if we do get pods in this namespace, we have nothing in there. So let's deploy the complete app in here. Let's deploy all. Yeah, so this is complete. This is not the split app. There's a complete app, including the catalog service into the cloud. Perfect. So we can look at this. It's all working fine. They're all up and running, great. So if we go back to Avi, and you would be seeing that we immediately added another endpoint, which is the cloud endpoint now to the endpoints of the GSLB service. So it automatically happened behind the scene. What happened is TSM figured out there is a shopping application, which was a public service, which got deployed in the cloud, and we went ahead and configured Avi to enable GSLB for that use case, right? Now, at this point in stage, you can bring down the cluster, the site, or the service, and we should be still up and running, right? Let's try to dig and see how this is behaving. So if you can see, we are right now going to just a single cluster because the health check is still not up and running. It takes some time. If you look at our health monitors, we only enable health checks to be successful once you do 3 successful checks at certain intervals. So there are tens of seconds before it gets it up and running, right? And you can see it's already up and running in one side. It'll take some time to sync on the other. And if we go on to dig, you can now start seeing that it's round robining based on the algorithm, default algorithm that we have right now to both these clusters, to A9 and AF, right? So this is working fine. Now let's try to bring down the service, right, and see the effect. And this is going to be interesting. So we'll take 1 minute into doing this before we end this demo, right? So let's scale the shopping service down. Let's make its replicas to 0. So what we're doing here is we're scaling the shopping service on cloud down to 0, right? As soon as we do that, you can see we just had 1 split second of service unavailable, 1 request failed, but all the requests are still passing, even if they're still going to 2 different cluster endpoints, because as I said, GSLB will take some time before it figures out that the endpoint is down. But somehow magically, our service is still accessible on both the sides. How did that happen? This happened because of the power of GNS. So as soon as GSLB got into that stage of black holing for some time, and we are still sending the request to this cluster, we figured out the gateway, and GNS figured out that the service does not exist on this cluster. But since all the clusters are in one GNS, we started routing it to the on-prem cluster. So even for that particular amount of time, we had service up and running. And this is a very powerful use case, right? Which shows the power of GNS, right? And as soon as Avi figures out that the endpoint is down, you will now see, as you're seeing, it's only going to the on-prem cluster. And if you go to the GSLB graph, you will see the 3rd cluster here, right? As you're seeing, and you can see how all these services are connected to each other. And this is the point which I was trying to make, right? In one case, the cloud actually did send from the gateway itself to the shopping app on the on-prem. That was those few seconds of time where the requests were coming here, but there was no service here, right? If we just stop our traffic and we go back to our on-prem cluster, we can see that we are scaling down. We will very shortly figure out that it is, as you saw, there was a 60-second grace period. We will automatically scale down. Auto scaling will trigger in and will scale down. Well, with this, we come to the end of the demo. So let's go back to our presentation.
Yep. So Manish, are you ready to answer some questions?
Yeah.
From the audience. So let me start out with some technical questions first. You showed cloud bursting. Is that being done by Avi or TSM?
So it's a mix of TSM and Avi, right? So what TSM does is, as a part of the GNS, enables us to cloud burst into the other cloud, where we can deploy application to the other cluster, which is residing in the cloud. But what it does behind the scenes is it goes ahead and configures Avi to enable us to route traffic to the different clusters, right? By configuring the endpoint as we just saw to the other cluster. So it's a combination. So this is the part of the combination of RV and TSM together.
Yeah, another question we have is from Alan that he's asking about the auto scaling. Where do you set the auto scaling settings?
So you set the auto scaling settings on the cluster as I showed you with the definition of the ASD. So that's just a YAML, and you define your YAML for your services, and you just apply that YAML on the cluster. And this can be applied per GNS in the next release. In the next release that we're coming, you can just attach it to a particular GNS through a GNS construct too.
Okay, thank you. And then we have this question, I can take it. It's asking about how to purchase these two products. So Chris, I think today, as of today, you can purchase two products separately. So you can log on to VMware website and you will see the different license options. But there is something that is coming up very soon that should make it easier to order the two products together. Stay tuned. We will have an announcement out soon. We can't talk much right now in this webinar. This is more focused on the functionality of the two products, but we will inform the public about how to order them together. All right. So that's all the questions we have. And Manish, thank you very much, and Bhushan, thank you very much for your presentation and demo. As a next step, we will send the recording of this webinar out to the audience, including the slides. And feel free to contact us for any questions at avimarketing at vmware.com. We're happy to address any questions you have. Okay, thank you, and everybody have a great day.
Thank you. Thanks, everybody. Thanks.